Hello and welcome to this last video in our lecture on hash-based cryptographic primitives. In this video, we're going to wrap up our discussion of HMAC by discussing its security and its efficiency. So remember that HMAC is an example of a MAC algorithm, and as such, it takes two inputs, a message M and a private key K, and then of course it outputs either an authentication tag or sometimes called a message authentication code or MAC. So the main design feature of HMAC is that inside of it, it contains a hash function with a lot of complicated, semi-complicated features around it, which we discussed in the previous video. But because HMAC is built on top of a hash function, the security of HMAC is going to depend on the security of the hash function that it uses. And so one reason HMAC is and has been very popular is because the researcher who designed HMAC were able to prove a very strong relationship between the security of the hash function and the security of the HMAC algorithm. So in general, the security of a MAC function depends on whatever information is available to the attacker, as well as the amount of resources that the attacker has. So suppose Alice is sending messages and authentication tags to Bob. So using a particular key K, Alice is going to send message 1 with MAC number 1, and then message 2 with MAC number 2, assuming she's using the same key for a while, and then message N and MAC number N. So the attacker has access to these, say, N pairs of messages and MAC codes. And the attacker has available to him or her a particular amount of time or computational resources. And so in general, the way we evaluate or assess the security of a MAC function is to give a probability of being successful in forging a MAC given or relative to the amount of resources available and the number of these pairs. So in essence, what the designer or the designers of HMAC were able to prove is that the amount of work that an attacker is going to have to perform is going to be either as much as a brute force attack on the key, which would take approximately 2 to the size of the key amount of work, or to do a birthday attack on, remember, the length of the output of HMAC is n, so the amount of work for a birthday attack would be 2 to the n over 2. And so in summary, what they proved is that HMAC is as strong, at least as strong, as the hash function that it uses. Now, when it comes to the other important requirement for HMAC, which is its efficiency, we have to look at the following questions. Since the main operation in HMAC is the execution of the hash functions, all the other operations are very fast, be it, say, XOR operation or appending bits to another block. These are all very fast compared to the execution of the hash function. So the efficiency of HMAC depends on how slow or how fast the hash function is. So the first question we want to ask is how many hashing operations are performed? Well, for that, we need to remember the algorithm. So remember, the HMAC algorithm starts with K plus after the padding, and we're going to do an XOR of the key with the input pad. Notice the output of this operation is exactly one block. This block is prepended to the message itself. So we start with the message M. we insert in front of it an extra block, and the first hashing operation is this one. So there's one hashing operation so far. Now the output of this hashing operation is a message digest of n bits. So in general, n is reasonably small. So you can consider that the size of this message digest is going to be about 1 or 2 blocks at most. Let's just say 1 block. And if it's not exactly 1 block, we can do some padding to bring it up to 1 block. And so remember, the next step in the algorithm is to prepend in front of this block whatever you get by XORing the key with the output pad. Okay? So when you take this block that we put in front and whatever the H function returns, we are left with only 2 blocks. And these are the 2 blocks that we hash. And this is the second hashing operation in HMAC. So the first answer is how many hashing operations are performed by HMAC? The answer is 2. There's 1 here and 1 here. However, it's not enough because the hashing takes a different amount of time depending on how long the message is that you're hashing. So the next question is, how long does each hashing operation take? And for that, we have to remember that these hash functions is a block-based function. So the time it takes to hash the message is proportional to the number of blocks in the message. So the next question then we have to answer the second one is how many blocks are actually hashed? Well, and in particular, how many blocks do we have to hash compared to the number of blocks we have to hash when we just hash the message M? Because remember, the efficiency of HMAC, one of the design objectives was that the efficiency of HMAC would be not significantly slower than the efficiency of the runtime of just simply hashing the message itself. So notice, whatever the number of blocks are contained in the message M, there's only one extra block here that is hashed when doing the first hashing operation, since we're hashing the original message plus 1 block. So here we have the number of blocks in M plus 1, namely this one. Now remember, we said the length of this argument to the second hash function is actually 2 blocks. So here we're going to be hashing 2 more blocks. So the answer to how many blocks we're actually hashing is just the number of blocks in M plus 3. So to conclude this analysis of the efficiency of HMAC, we have to ask ourselves, is this computation going to be a lot slower than this one? And the answer is no, especially if the message M has a good length, meaning a good number of blocks. The overhead of computing HMAC, which is this computation here, this is HMAC run on M and K. The overhead of this computation is only going to be about the time it takes to hash 3 extra blocks. And that's pretty minor, especially, like I said, if M is large enough. So this concludes our evaluation of HMAC. It's a relatively fast algorithm. It's as secure as the hash function that it uses, and this explains why it has been so popular in the past few years.